All right, guys, this is Anatomy Physiology Lesson 10.04, over voltage and current. These are some topics that you have to have a basic understanding of in order to understand how nerve impulses get conducted down a neuron. But I have a quick, I should have probably thrown this in the last video. It was either going to make for a really long video, so I'm going to tack it on here, and I'm going to just bring this down. I want you to flip to this sheet in your packet. And I told you in the last video, we were talking about central nervous system. So we've seen these before. This is a neuron in the peripheral nervous system. PNS is peripheral nervous system. And the only glial cell that we're going to talk about in the peripheral nervous system. So the Schwann cell is a glial cell, but it's a glial cell that's in the PNS. And I wanted to contrast this to the oligodendrocytes in the last video. So what we see here is the same diagram we had in 10.02. We've got our nodes of Ranvier, we've got our myelin sheath. So if I take all of these Schwann cells together, all of the fat on this axon is the myelin sheath. Over here, I see one Schwann cell, and here's my nucleus, and you can see that it has layered up. So it grows this direction, it grows around the axon and creates these layers. But only one Schwann cell for one section of myelin, and it can only myelinate on one axon. So this is a little bit different than the oligodendrocyte. The other thing I wanted to look at quickly are some categories of neurons. So here I have my cell body, CB, CB, CB. And this is what we looked at before. This is what we think of as a typical neuron, and that's called a multipolar neuron. We have we have lots of processes coming in and going out. So here I've got 1, 2, 3, 4, 5, 6, and there's usually more than this, but here I have 6 processes going in and going out of the cell body. That makes it multipolar. Here, I only have one cell body, or one process coming out of my cell body. I still have receptors here and receptors here. I still have an axon. I still have a direction. So my nerve impulse directs here, comes in here. But here my nerve impulse travels down the axon like this, and I have one process coming out. So we call this a unipolar neuron. Here, the cell body's in the middle. So here's my direction of my nerve impulse, but I have a process here and a process here. So I have 2 processes. So we call this a bipolar neuron. But this is just to illustrate neurons come in a lot of different shapes and sizes. And this is just kind of the tip of the iceberg. We have all different, especially when we get into the central nervous system, then we have different neurons. But so they're saying that this is a sensory neuron. This is an example of a neuron. You might have a touch neuron in your skin. This is one that's going to go between 2 of these. Lots of different shapes and sizes. The only thing I expect you to know is bipolar, unipolar, and multipolar. All right, so with that, let's get to the topic for this video, which is voltage and current. Before we talk about voltage and current, let's review things of the concept of potential energy. So you have to first understand potential energy. In 6th grade, 7th grade, 8th grade, your freshman year, you talked about potential energy versus kinetic energy. And we define potential energy as, in general, potential energy is the ability to do work. The ability to do work. Now, the work that you're doing depends on what you're talking about. If you're talking about mechanical potential energy, it's the ability to move something. If you're talking about electrical potential energy, you're talking about the ability to move a charge or something with a charge. So kinetic energy, on the other hand, is energy of motion. So there's electrical kinetic energy, in a sense. There's mechanical kinetic energy, thermal kinetic energy. molecules moving is thermokinetic energy, that's heat. So potential energy is the ability to do work. So let's talk about mechanical first. And a good example is a water tower. So we have a higher potential energy. The water that's up in the tower has the ability to do work when it falls. And so let's say we had an old-timey water wheel on here. Let's say that let's add a. So as that water falls, it turns the water wheel this way. And then maybe the water wheel's attached to a grist mill where we've got stones. And we can put our grain here. And as the water falls, our grain gets ground up in these grist mill stones. So we've done some work. And that happens because the water will always go from a higher potential energy to a lower potential energy. Well, if this is a tank, once the tank's empty, our work stops. So does that mean that it'll automatically go from lower potential to higher potential? Yeah, no way. Unless you go to Hogwarts School for Witches and Wizards, this water is not going to Leviosa up out of the tank up here. We have force. So to go from low to high, this happens automatically. To go from high to low, I misspoke. To go from high to low, that happens automatically. To go from low to high requires energy input. And that happens in the form of a pump. So if I want to get my water back up to my water tower, I have to pump the water up there using electricity. So my energy input to get the water back up would be electricity. Here I have a puddle, and that's completely at zero. So ground potential would be zero. And we give it numbers. So we say the lowest potential is zero. So in this case, well, it doesn't matter if we're talking about water or if we're talking about electricity. Electricity behaves the same way. Let's again back up just a little bit and what are we talking about when we say electricity? Electricity is flowing charges. All right, well, we keep doing this when we're talking about things and we maybe haven't defined all of the terms. So what's a charge? Charge is an inherent base function of nature. Something either has a charge or it doesn't have a charge. If it doesn't have a charge, it's neutral. So if we have no charge, we're neutral. If you have a charge, so if a charge is present, you can have a negative charge. And I always put this in parentheses so that you know that I'm not just doing a dash. Or you can have a positive charge. That's it. Two types, positive and negative. Well, what's an example of a negative charge? Hopefully, if you don't remember it from chemistry, or if you're in chemistry now, or you'll remember it from your previous classes, we talk about electrons as being negatively charged. So they have a charge of -1. What's got a positive charge? Protons have a positive charge. By the way, neutrons are neutral. Neutrons are neutral. But those aren't the only particles that have charges. We talked about this back when we did the physiology of muscles. We saw that calcium has a +2 charge. I don't remember if we talked about it or not, but chloride has a -1 charge. By the way, it's good to know your abbreviations in this chapter. So calcium is always going to be Ca +2. Chloride is going to be Cl -1. And the one that is super duper, super important in nerve impulse conduction, or I should say the two, are sodium, which is +1. So we write that as Na +1. And potassium, which is also +1. So if I can cause sodium and potassium to flow, so if I have a flow of Na +1 or K +1, folks, that's electricity. Every nerve in your body has flowing sodium and potassium. Every nerve impulse that is conducted from your brain out to your hands, as I'm writing this, my brain is continually sending impulses out to my hand. It's sending feedback back to my brain. How's that happening? We have flowing charges, sodium and potassium. Just like water flows, charge flows just like water. And just like water, it doesn't flow randomly. It will automatically, I'm going to circle this in red. See, we're going to use terms here called voltage. It'll automatically flow from higher potential to lower potential, but to go from lower to higher requires energy input. Well, in physics, we don't really say electrical potential energy. Or the term, a better way to say it is the term for electric potential energy is voltage. So what that means is that here we have water flowing from higher in its gravitational potential energy to lower gravitational potential energy. In an electrical system, charge will automatically flow from higher voltage to lower voltage. So in an electrical system, charge flows from higher voltage to lower voltage. For charge to go from lower voltage to higher voltage requires energy input. To go from lower voltage to higher voltage. Requires energy input. And what is it that's flowing? In this case, it's sodium and potassium. Again, we talked a little bit about the role that calcium had in muscle contraction, but in our purposes, I'm going to circle this in red. We're talking about sodium and potassium flowing. And they're governed by these rules. So let's do a takeaway here. All right. We started off with something we're familiar with. We started off with water, and it flows from a higher elevation or a higher potential energy to a lower potential energy. And I don't think I said that expressly. I should have. Elevation is what gives us, water always falls down. So that elevation, higher than our ground, gives us that potential energy. And it'll automatically flow down, but to go back up, we have to put in energy in the form of our pump. We have to pump it back up. Talking about electricity, it flows just like water, but here we're talking about things that have charges. In your walls, we have electrons, but in your body, what we have flowing are sodium and potassium ions. Those are governed by voltages. So voltage is the electric potential energy, and charges will flow from a higher voltage to a lower voltage automatically. Let me add that in here. Automatically But to go from lower voltage to higher voltage, we're going to have to put in input. And think about it. What is the energy that your body has used? And we learned about from biology almost on day one. It's going to require ATP. All right, that's your quick crash course physics over voltage and current. Thanks for watching.